Hello. Uh, in this video, we will see some examples of the large signal analysis, large signal model of the 5 transistor OTA. So basically, we are not going to see the small signals, but in term of large signal. That is, if the inputs are swing is higher, then what will be the output voltage and how we can see the things. So for example, this is the characteristics we know that this is the characteristics of that 5 transistor OTA. Now for example, let's say this is minus 300 and 300 millivolt, after before which the output is 0 and after which the output is VDD. Okay, it's not exactly VDD or it's not exactly 0, but near to the VDD and near to the 0. Then we can see here closely, look here, that the output is defined either VDD or 0 depending upon the difference in the input. Okay, when the difference in the input, let's say if the difference in the input is 300 millivolt and minus 300 millivolt, then we can say that the output is 1 or 0. So this is the first thing, that output is single-ended high or low depending upon the differential input. What is the input difference, either above 300 and minus 300. So if you want the signal from double-ended to single-ended, and if you want the signal high swing or low swing, basically rail to rail, then you can use this device, this type of 5 transistor OTA. And one more example, we add one inverter in between the output, actual output, and output from the OTA to get the complete swing, VDD and ground, because here it is not completely VDD and ground. Okay, it is there is an inverter buffer added after the devices for complete swing. Okay, now let's go for the another example. Okay, so here question is simple. They are asking that if this is same V in, what is the V out when VDD is decreased? So if you see here closely, I'll tell you simply in that simple term. Okay, when VDD decrease, obviously this voltage will decrease. So yes, it is decreasing, but problem is when V out is decreased, this M2 will go to the linear region, and when it will go linear region, your figure will become like this, because it's a resistor, it will transform into the resistor. Okay, so till now your voltage, as the voltage VDD decreases, your V out decreases, so something like this. Okay, now we know that since this voltage is decreased, okay, this voltage is V out is decreased, and what will happen, we have same current, I is fixed, VGS minus VT and multiplied by VDS, because linear region. So as this is fixed and this VDS is decreased, this VGS has to increase. So that is why if you see here, the source voltage will go where? Down, because as VDS, this, you know, this voltage if goes down, VDS goes down, but for the same current VGS has to increase. So that is why this voltage, what will happen, this source voltage will go more down. Okay, now since the source voltage will go down, what will happen, this M5 will go in a linear region. So till M5 goes into the linear region, the characteristics will be defined by this figure. The characteristics will be defined by the figure, that when the transistors are in M1 and M2 are in linear region. Now if you see the fourth point, when the source voltage of M2 is such that the saturation condition of M5 is such that the VDS of M5 is less than the VD sat of M5. In that case, if you see, the M5 transistor is now working as a linear region, and then if you see the point number 4, from there you see this is also again in the linear region, and this is resistance. So the characteristics of the V out will be defined by this figure. Okay, so as the VDD decreases, V out obviously decreasing, but the decrease in the voltage is defined by the how the figure is. Okay, and earlier the linear decrease in the current was there, but now once this is the current source become linear region, this current is not fixed. So if current is not fixed, then the current will be defined by, voltage is defined by the IR, and this voltage is defined by how? This defined by the V upon R is I, and V is decreasing, and R here, if you see here, is also decreased value. Okay, so the V out will be defined by this circuit. Okay, so point here is just to analyze that our voltage value is decreasing, and how the circuit will be transformed from saturation region to the linear region, and how the MOS is transformed from the current source to the resistance. Okay, and once this voltage is less than the VTH of the M3 and M4, then it will be goes to the off, and so the V out will be 0. Okay, so simply understand this in term of the how the circuit will be transformed. Okay, now let's go for the one more example. Here what I did, just connect the V out and V negative, then this is the figure for this case. For this case, let's see the analysis. Okay, simple. Once this is 0, what does it mean? It means M1, M3, M5, M1, M3 and M4 are in off state, and M5 is in deep triode. Why? Because there is no current from M1 to flow, and there is no current from M4 to flow. M1 and M4 no current, so there is no current from M5 to flow anywhere, so that is why VDS of M5 is 0. So this voltage is 0, and since we know this voltage is 0, and because of this there is no current, what is this voltage? This voltage will be 0. Why? Because there is no current, VGS will be 0, so V out is 0. Okay, now let's go. If we increase the V in, what will happen? If we increase the V in, obviously M1, M3, M4 will have some current, M2 will be on. Why M2 will be on? Because since M4 has some current, M2 is just a diode connected thing. Okay, so there is some VGS developed here. Okay, and this MOS M5, since M1 is on, there is a current to flow available. Okay, so from both the branch current will flow, and there is some voltage VGS developed, and this voltage will be increasing. Okay, some voltage is developed, it means some from 0 to it will increase to some voltage. And important point is, since M1 V in is small, we can say that it is in a saturation region, M1 and M2. Okay, now if we increase V in, what will happen? Where is the danger? Danger is, if the input voltage is increased, M1 and M4 will go in a linear region. Why is that so? Because M3 and M2 are diode connected, so there is no issue for them. M1 and M4 will go in a linear region, and if you see, the M1 VD should be greater than V in minus VTH, and VD is VDD minus VGS of 3. So from there you get this equation. And if M4 is going into the linear region, before that, for saturation condition, VDS of M4, that VSD of M4, that is VDD minus Vout, should be greater than the VSG, that is of M4, minus mod of VTH. From there you get some equation. So this is the equation will help you to understand that what is the Wien condition we have to make. Okay. So, but point is, in this case, when Vn and M1 and M4 are going into from saturation to linear, let's see how the characteristics of the circuit will look like. So this is also linear, this is also linear. What is it the meaning of linear means? Linear means VDS is low. Okay, the meaning of VDS. So this VDS M3 and M4, since M4 VDS is low, current in M4 is less. Simple. So what does it mean? If the current of M4 is low, VGS of M2 will be low. Okay. Also, since we have increased Vn very high and this is linear, VGS of M1 is higher than the VGS of M2. Okay, gate voltage. So basically M1 current is high than the M2 current. So, and linear region, because of the linear region, we have gate voltage higher. Okay, so VGS1 is greater than the VGS2. From here we can say that VG1 is greater than the VG2, and so the Vout is less than the Vin. So after it is going to the M4 goes from the saturation to linear, Vout is less than the Vin. So there is some difference. Okay, so this is the basic characteristic of the unity gain amplifier. So you have to from this way we can analyze some last signal analysis of the transistors, last signal analysis of the 5 transistor operation transconductance amplifier. So this is the very basics of the way we can analyze the circuit. Okay.